Okay,
I have a professor.
Yeah,
I
go
have
ahead.
a question.
Yeah.
Is the secant method the same as Newton method? The equation look I think like the same.
Almost similar, but not, because in Newton method, you need the actual derivative of the function. So for example, it's Koi, right? That who is asking the question? Who is asking this question?
Yes.
Koi, right? Yeah.
Yes. Yes.
Okay. So generally what happens that in Newton's method, you actually start with the first initial guess and you try to draw a tangent to the function for that specific x naught, and that tangent line is what is basically required. So in Newton's method, generally the iteration are xi is equals to, or xi is xi minus 1 minus f xi minus 1 divided by f prime of xi minus 1, if I'm not making mistake. You can check that. So basically this is what in Newton's method, this specific function is analytically derived. So for example, if your function is f of x is, let's say, sine x minus 2x, for example, say, then you need to have this as f prime x as cosine of x minus 2. But in case of secant method, what happens that you don't need to know this specific, there is something I'm missing here, I'm not sure. Maybe it's right, but I'm not very sure if I'm missing any specific term here. But okay, in secant method, you don't need an analytical expression for f prime x. You basically replace it with a specific derivation or specific definition of f prime on how to calculate the slope. And that is nothing but f of xi minus 1 minus f of xi minus 2 divided by x is y1 minus y2 is x1 minus x2, or you can reverse that. It doesn't matter. So you are not calculating, you see here, you're not calculating this f prime x explicitly in secant method. So in secant method, you are basically taking another point and then you are approximating the derivative of the function. That's the difference. Does it make sense, Corey?
Yes. I thought in Newton method I used the slope formula, so I see it now. Thank you.
Okay, got it. So both are using this slope, but in Newton's method, you need an analytical derivation or analytical function. And in secant method, you are not using this function. You are basically approximating it using a finite difference formula. It is a first order finite difference formula. When we'll be doing that, you will actually get to see. And it is simply just slope of a line. It is just a slope of a line is y2 minus y1 over x2 minus x1. That's what it is doing. So
sorry, another question. So
yeah,
in MATLAB, how would you find the derivative? Do you use like a built-in function for Newton method?
I don't want you to have a built-in function. Use whatever function is derived with or derivative and use this function instead.
Okay, so I have to find the derivative first.
Yes.
Okay.
Yeah. So okay, so another thing, I guess there in my notes in the secant method, not the secant method, the regular falsy method, when we are doing, we actually were using, if you remember, we are using this 2-point interval. It is a bracketing method. And I probably have given you some expression for finding the point C. This is regular falsy method. And this is 2 points, which actually brackets the root. And to find the point C, we were basically using the equation of a straight line, which basically is that y minus f of A is x minus A, f b minus A and b minus A. And basically we need to find the point C where y is 0. So y is 0 and x is C. So if you have to solve for that, you basically will get x is equals to a plus y minus f of a times b minus a divided by f of b minus f of a. And when you substitute c, x as c and y as 0, you basically are getting a minus f of a, b minus a, or fb minus fa. So when we are doing this derivation, somehow I think that this ratio was reversed in the derivation. So Khoi actually pointed that to me, that during the class notes we actually get this ratio reversed. So please correct that in your notes. So thank you, Khoi, for bringing that to the attention. So the midpoint of the C should be actually a minus f of a times b minus a divided by fb minus fa. So this is basically reversed. Okay, so having said that, let's start with the matrix operations. And I asked you guys to read chapter number 8. How many of you have not done that?
Not completely.
Okay.
I couldn't finish.
Yeah, that's fine. I mean, if you cannot finish it, but if you have read that chapter and if you've gone through the chapter, you probably have come across many familiar terms, isn't it? Like finding the determinant of a matrix and finding the inverse. Am I correct, guys?
Yes, yes.
Yes.
Yeah, you're correct.
Yeah. So for example, I'm just revising or reiterating or recapturing some of the concepts there. So let's say I have a matrix A, I'm just 2 minus 3, 0, 1. So how can you find the determinant of that?
Just two.
Just 2, and you know how to do that, right? So basically, you find, so before I actually write the determinant basically is given by this symbol, where this basically the open bracket, not the bracket, it's just like a sign of mode, but in matrix operations, this is basically representing determinant, and determinant here you can easily calculate as this, where 2 times 1 negative cross multiplication. So you multiply this number with this, and then negative, then you multiply this number with this, and whatever the result, that will be your determinant. Now this is just for 2 by 2. If you have a 3 by 3 matrices, 2, 1, 0, minus 1, 3, 2, 4, 5, 0. So if you have something like this, which is 3 by 3 matrix, the determinant will be again similar like that. But what you have to do is you have to be careful about some of the signs. So you basically take this number. Generally, it is the formula for calculating the determinant is, let me write it down. It's A I K minus 1 I plus K M I K, where AI K goes from 1 to n. So this is our n by n matrices. Determinant is generally we actually calculate, or we can calculate or define for square matrices. So for n by n is 3 by 3. So K goes from 1 to n, Aik representing the element of ith row. So if I can be any row here, 1, 2, 3, any row. So if I take I as 1, so A1, 1. So it will be this number times minus 1 raised to power I plus K and MIK. MIK is basically the minor of minor corresponding to this element. So this is called as minor. And the way it is obtained is, if I'm saying that if I expand this summation, I actually get A11 minus 1, 1 plus 1, M11 plus let me minimize this. Okay, A12 minus 1, 1 plus 2, M12 plus A13 minus 1, 1 plus 3, M13. And what is M11? M11 is basically obtained by eliminating first row and first column. So eliminating ith row and ith column. Oh, sorry, ith row and kth column. So first row, first column. If I eliminate first row and first column, I get 3250. So M11 is basically 3250. M12, can somebody help me to find out what M12 would be? Let me actually instead randomly pick a student from the list. So Chavisa or Chavisa, sorry, I'm pronouncing not correctly. Okay. Yeah, can you help me to find out what M12 would be? I believe your mic may not be working, so you can say what should be the elements, and I can write it down. So what should be the first element? -1, 3. Okay, so first row, second column, -1, 2 actually. So when I say M12, M12 will be first row and second column. Whatever is left will be the minor. So -1, 2, 4, 0. That should be the minor. You eliminate ith row, first row, second column. So eliminate that, whatever is left, that will be your minor. Similarly, M13. M13 will be eliminating first row and third column. And what we actually get -1, 3, 4, and 5. So what you are actually saying, Savisa, is about M13. And M12 will be basically first row and second column. Remaining is -1, 2, 4, 0. So, okay. So I believe everybody is getting that so far, right? Am I correct, guys?
Yes.
Yeah. And A11 is nothing but the coefficient here. This is A11, this is A12, first row, second column, A13, first row, third column. So you will see A13 0, so automatically M13 element or this specifically will go up. Now, to find the determinant of that, you know how to find a determinant of 2 by 2 matrices, which we actually saw it here. So when you get M11, which is a 2 by 2 matrix, you know how to find the determinant of this M11. And that will basically be replaced here. And that's how you calculate a determinant. Now, this is for 3 by 3, or you can go for any number, basically. You can go for 4 by 4, 5 by 5, the computations remain the same. This is basically the generic expression for calculating the determinant of a matrix. Am I making sense, guys? Is everybody with me?
Yes.
Yeah.
Yeah. Any questions so far?
So the minor that you use in the equation is just the determinant. So when you have A11 -1 to the 1 + 1, and then times the minor 1, 1.
Yes.
That's
Minor
the
one is the
determinant.
determinant of this matrix. Yes. Minor is basically the determinant of this matrix. This 2 by 2.
Gotcha.
Yeah. So it is a determinant of this matrix, and so on and so forth. So let me actually write determinant here. Determinant, determinant, determinant. Okay. DET basically is determinant of this matrix, determinant of this matrix, determinant of this matrix. Okay, so if everybody is good so far, so I just said that this is a minor. Minor is basically the determinant of the matrix obtained by eliminating ith row and kth column. Now, if you look at the combination of this is called the cofactor. This specifically, this two term -1 raised to power I plus k times this is your cofactor. This is called the cofactor of AIK, of the element corresponding to AIK. This is called as cofactor. -1, the whole, actually, it is minor is only this much, and cofactor is this much. The whole of this is cofactor. Now, the reason the cofactor is important is, excuse me, when you need to find the inverse of a matrix, then this cofactor will be useful to find the find the inverse. So this cofactor is basically CIK, represented by CIK, and it is nothing but -1 times raised to power I plus k, where I corresponds to the row, k corresponds to the column, and MIK. MIK is the minor. Minor is the determinant of the matrix obtained by eliminating ith row and kth column. Is everybody with me so far?
Yeah.
Yeah.
You said it was important for finding, you said, the inverse, right?
Finding the inverse. So let me say if I have to find the inverse of the matrix, so you basically, there are several ways. So one of the ways that we have seen or we have learned in our basic maths classes is you use the adjoint of a matrix and you divide it by the determinant of the matrix. So A inverse is adjoint of A and divided by determinant of A. Now determinant of A, you know just how to find a determinant of A. Now adjoint of A is basically a matrix which is obtained by this cofactor. So C11, C21, C31, C12, C13, C22, C32, C23, C33. This is the cofactor. This is basically the adjoint. And divided by determinant of A will be your inverse. Now what is C11? C11 is basically nothing but the cofactor that you obtained using this, where C11 will be -1 raised to power 1 plus 1 and M11. And M11, you know, it is basically determinant of this matrix, which is just -10. This is -8. And this is -5, -12 is -17. Okay, are you guys with me, guys? Yeah.
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 So I'm just quickly refreshing what we actually have learned or we actually have seen so far, how to calculate A inverse or inverse of a matrix. Inverse of a matrix is using the adjoint, and adjoint is nothing but the cofactors arranged in this manner. Now you have, if you are using this to write a code or MATLAB code, you must have to remember that generally the first index or index here represents a row, the second index represents a column. So if I am basically referencing any matrix elements, I generally reference it like that: A11, A12, A13, A21, A22, A23, A31, A32, A33. First row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, and so on and so forth. That's how basically the indexes or indices are generally referenced to, or basically are referenced. But in this specific cofactors, you basically need to know that these are not arranged like C11 and C12. This is C11 and C12 are basically arranged in a column manner. So that is the only thing that you have to be careful about while finding the adjoint matrix. So the adjoint matrix, the elements are somehow basically transpose of the regular order that we generally use. Typically, that is how we actually reference any element of a matrix. So if I say what is the second row and third column, so what is the second row and third column element, and it is basically this second row, third column, that is this element. But when we are doing the calculating the inverse and finding the adjoint, then basically the second row and third column will not be here, but actually it will be here. So it is just a transpose of what the regular order is. So that is.
What was the formula for the cofactor?
Formula for the cofactor is basically represented here. It is -1 raised to power I plus k. It is just the same, the whole expression here.
And you said I is the row?
I is the row and k is column.
Okay.
So I, row, and k is column. Okay.
All right. Thank you.
So everybody's with me so far?
Yeah.
Good. Any questions, guys? Okay, so if not, we will start with numerical solution for matrices, basically involving matrices. So the first solution technique that we are going to use is called Gaussian elimination. You guys have read about it so far. So what we actually do in Gaussian elimination technique to solve Ax is equals to B, where A is a matrix of, we are starting with, let's say, square matrix. It need not be square matrix. X is a vector which has got the order of, or which has got the element in n by 1 vector, n rows, 1 column. B is also n rows, 1 column vector. So B is a vector, A is a matrix, and X is a vector. Unknown. X are unknowns. A is basically the known coefficients. So let me actually take one textbook example. Just give me a second. So one of the textbook example, I'm just taking one textbook example where, let's say you have this system of equation, minus 3x2 plus 5x3 equals 0, 6x1 plus 7x2 minus 3x3 equals 2, and 2x1 minus x2 plus x3 equals 6. Okay. So this is basically an equation that just one, it need not be all the same equation, it can be any equation, but it is a system of equation where it has got 3 unknowns and you have got 3 equations, right? And that's what if you have to solve, how will you solve it? Now it need not be only 3, it can be 4 and 4 variables, it can be 5 variables, 6 variables, depending on the system that you are solving. For example, if you are using a finite element solver or if you're using a CFD solver, they are using 1000 by 1000 depending on how many nodes you have in your specific specific system. So they are basically solving the equation as kx equals 5, or sorry, f. Therefore, it is a load vector, this is a stiffness matrix, and these are basically the displacements. So this is a load vector, this is displacements. Actually, it is k times u. These are displacement, unknown displacements. This is stiffness matrix. And this is a load vector, applied load vector. And generally, when we're talking about this, you generally are not getting this system of equations as it is. I mean, nobody is giving you, you are basically, or the solver actually setting up this system of equations by, for example, if you are using a finite element solver and there is a cantilever beam and you are applying a load, and you are basically having, generally when you apply, use finite element method, you discretize it into different elements. So let's say there are different elements. This is first element, this is second element, this is third element, and so on and so forth. Then what this, what the solver and what the finite element solver does, it actually takes the stiffness matrix of individual elements. And let's say it is K for first element. Then this is stiffness matrix for first element. For first element. Similarly, you have K2, which is the stiffness matrix of second element, and you keep on calculating the stiffness matrices, and then you basically assemble them into a big stiffness matrix, which has got K1 component, K2 component, and so on and so forth. That becomes a big stiffness matrix. And the U's are basically the displacements of each individual element. So U1, U2, and so on and so forth. And then you have force vectors, which is 0, 0, 0 till you apply a load minus P at the end. And the last element you are applying the load. So that is basically the system you actually get in physical application. So this is just for mechanical. It's an example of a mechanical load or mechanical finite element methods where you're actually solving a big system of equations and you're interested to find the displacement. Now, when you are doing these calculations, you are not doing this only once. If you have to do it multiple iterations, suppose it is a nonlinear system, or suppose P is a time varying load, then for every time increment, you have to solve this system of equation. It can, and it need not, it will not be just like 10 elements. It can be 1000 by 1000 or 10,000 or 10,000, depending on how many elements are there in your model. So if you have a fine mesh, this system will keep on enlarge. So basically you get a very large matrices and you need to solve the system of equation, which is represented by here. So one of the system or one of the technique to solve this system is called as Gaussian elimination. It is a very basic technique to solve the system of equation. There are other techniques as well we will learn during this discussion. So initially what we are basically interested in how the Gaussian elimination helps to find the solution for that. So to do that, if you have read that chapter, you probably have come across an augmented matrix. So the first step that we do is create an augmented matrix. An augmented matrix is nothing but you basically combine A and B together. So this is just a partition to say that they are basically separate, but they are combined together. So I have A and B written together. So what is my A matrix? So A matrix is basically given by, let me ask actually randomly again. Kenneth, Nim?
Oh, sorry. Hello?
Yeah, so can you help me to write what will be the elements for the A matrix?
According to those equations up there on top of it?
Yes.
-4.
Yeah.
-30.
3.
5.
5.
And the B area is 0.
0. So
And then it's 6.
7 minus 3, 2. And 2 minus 1, 1, 6. So great. So basically you are writing the coefficients here. So whatever the coefficients of x2 is, that goes in here, x3 coefficient goes in here, and the B vector goes in here. So this is what you call as augmented matrix. Now in this, you actually do some elementary row operations. Perform the generic elimination technique is you perform elementary row operations to create an upper triangular matrix. And I hope you guys know what the elementary row operations are, upper triangular matrix. So elementary row operations basically means is represented by ERO. So first element, one of the elementary row operation is you multiply a row by any non-zero constant. When I say multiply a row, that means the entire elements of this row. So I can multiply this row by 2, 3, -4, -6, whatever number you can, you like. You can basically multiply. The system of equation will not change. So the elementary row operations are basically such that you perform these operations and the system of equation will not change. It will remain the same. Elementary row operation second says you can interchange two rows, any two rows. And the elementary row operation third is that you can multiply a non-zero constant to a pivot row and add it to any other row to eliminate the variable, to eliminate variables. Just say eliminate variables. So basically it says that I can multiply any row with a non-zero constant. I multiply this row with, let's say, half, 0.5, and add it to this row. Then I will eliminate the variables corresponding to x1. Are you getting what I'm saying here, guys?
Yeah, I follow.
Yeah.
Is there anybody who is not following it? Please ask. I will be more than happy to explain you again.
Can you please repeat like the third step?
Third step says that you can multiply a non-zero constant. Actually, it is not to a pivot row. I'm basically adding this word because that's what we will be learning now. In general, this pivot is not there. You can basically, it says you can multiply a non-zero constant to any row. So I can multiply this row with a constant. Let's say I multiply this with 0.5 And when I multiply this with 0.5 and take this row and add it to this row and replace the results, what do I get in here? If I multiply this with 0.5 and add it here, what do I get?
0.
0, right?
Yeah.
So basically when I add it, then basically that means the coefficient corresponding to x1 is eliminated in this third equation. So that is what this elementary row operation does. We will actually see, we'll actually go through this step and we will actually see what I actually mean by that. So you can multiply a row by any non-zero constant, you can interchange any two rows, or you can multiply a non-zero constant, add it to any other row to replace its coefficients or to replace its values. So that is also acceptable. That is also known as elementary row operation. Now we will see how to basically carry out this operation. So we will actually solve this equation using this Gaussian elimination technique. So before I actually go through this, so what you have learned in chapter number 8 is just simple Gaussian elimination technique, but what we are learning is we are combining our discussions with the numerical techniques, and we call that as what we were learning in chapter number 11. That's what I was basically combining those two chapters, because it is essentially the same, except here in Gaussian elimination, to make it more robust and more accurate, you actually use a technique called as partial pivoting with scaling. Partial pivoting with scaling. What does the technique does is, by the way, when we actually, I'm asking to do elementary row operations and saying you can use Gaussian elimination technique to solve for X. I just am curious to know, is everybody here in this class understand how Gaussian elimination works, simple Gaussian elimination technique works?
Yeah, I understand.
For the other students in the class, can you guys please?
Can you show an example yeah. Maybe if you could show an example.
Okay. So, the reason I was basically asking is so that I can explain you why we are doing partial pivoting with scaling and how it is different from other steps that are explained in chapter number 8. That is the basic Gaussian elimination technique.
Professor, is partial pivoting with scaling is another method, or?
Yeah, it's another method, but it is doing the same, using the same EROs, elementary row operation. So let me explain what it actually does. So what it does in this partial pivoting with scaling technique, what do? You actually look for, in only A matrix, not for the B matrix. In A matrix, you look for the maximum coefficient of A. So basically you look for the maximum absolute coefficient of x1 with respect to other entries in each row. Okay, so what we do here, we actually see for each row. So let's say I'm rewriting this equation over here so that I can show you the steps. I'm rewriting the steps here: -4, -3, 5, 0, 6, 7, -3, 2, 2, -1, 1, and 6. So what we do, the first step is, in each row, what I'm doing is, what is the maximum value in this first row, the absolute value that you actually see here?
5.
5, right? Is everybody with me?
Yes.
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 So what you do, you actually see all the elements corresponding to x1. What is corresponding to x1 are -4, 6, and 2. So what you actually do is you actually find which row is the pivot row. So what we are doing is selection of pivot row. Pivot row, and I will explain what I mean by pivot row. Selection of pivot row corresponding to X1. Selection of pivot row corresponding to X1. What it basically says that I'm basically trying to find which row I'm going to call as a pivot row and corresponding to X1. So corresponding to X1, the entries are -4, 6, and 2. So what I'm doing is for each row, I'm finding the maximum and just calculating what is my R1 for first row corresponding to X1. So it will be ratio of -4 by 5. R12 is, or sorry, R21 is, I will explain you just in a minute what is R21 is. So 6 by 7, and R31 is 2 by 2. So what I'm doing here is I'm trying to find what is the pivot row, which one is the pivot row. So in this row, I'm finding what is a maximum value, which is, let's say here 5. So I take the absolute value corresponding to X1 entry, which is -4. I take the absolute value of that and divide it by the maximum value of that row. So divided by 5. That's what I'm calling as R11. 1 corresponds to the first row, and the next index here corresponds to X1 variable. Does that make sense? Yeah.
Can you repeat that, Professor? Sorry, I missed.
It's okay. So the first index represents the row, first row, and so this is your first row, and second index represents the column, basically the entry corresponding to X1. So first index or first variable. So R21 is the second row. When the second row entry, second row and 1 corresponds to the X1. So second row, first column, third row, first column. You can say it's row and column. That's it. And we are interested in column number 1. This is column number 1. This is column number 1. And we are interested in column number 1 because we are interested to find the pivot row corresponding to X1. Is everybody following it or not?
Yes.
If
Yeah.
not, please let me know. I will try to explain again. I have no issues in explaining again, but please let me know if you are not.
Yeah, I got it. Thanks.
Is everybody following it?
So are we
Yes.
just comparing like the maximum coefficient of the X to the rest of the values on the row, or?
Come again, sorry.
So it's we were saying earlier that we're looking for the maximum coefficient, right?
Yes, maximum coefficient. So let me actually say what I'm saying. Maximum absolute coefficient of X1 with respect to other entries in each row. So that's what I'm saying. So with respect to other entries in each row, this is a maximum coefficient. And then I'm just taking that and finding the relative coefficient of X1 corresponding to X1. So this is -4 by 5. This is 6 by 7. This will be 2 by 2.
Okay, thank you.
Yeah. And if you calculate that, which one you think will be the maximum here?
R31?
Everybody agrees R31 will be.
Yeah.
R3, yes.
R3.
R31 is the maximum. So this is your maximum. So that means your third row is, this means the third row is your pivot row. What it basically means, you take this third row and you make it, or you interchange with first row. That is your elementary row operation number 2. If I show you, I showed you that elementary row operation number 2 is interchange. You can interchange any 2 rows. So what I'm doing here, I am picking this third row because that's what my partial pivoting, this specific technique of finding the maximum value of X1, relative value of X1 with respect to other entries, that shows that by calculating all these R values, I found that third row has got the maximum value of its coefficient. Then I interchange that. So when I interchange that, then the new equation will be written as I mean, if you interchange that, what you will get? This will go to the first row. So it will become 2, -1, 1, and 6. The second row remains as it is. And the third row will become this -4, -3, 5, and 0. Is everybody following it so far?
Yes.
Yeah? Is everybody getting that?
Yes.
Good. So that is what you actually do for the first step. And then you try to eliminate from all the other rows, eliminate the first entry corresponding to X1. So how can you eliminate 6 from this row? So let me actually ask somebody here. Quinton, Pam. Quinton. Okay, Victor. Victor, are you there?
Yes, sir.
Yeah. So can you help me to find the steps such that I need to eliminate a number and eliminate this 6 here from this row? How can I eliminate 6 here using my elementary row operations? Using these, any combination or any one of these, how can I eliminate 6 from this second row?
Could we add the first row times -3?
Yeah, so if you multiply the first row with -3 and add it to here, so what do you get? Can you guys tell me what will be the answer? So 2, -1, 1, 6. What will be the entry here? If I multiply this with -3 and add it to this row, what do I get?
0.
Then
10.
10, then
6.
-6, then
-16.
16. That's it, right? And the third row will remain as it is, -4, -3, 5, and 0. Is everybody with me so far?
I think it's -16.
-16, yes, you are correct. Is everybody with me so far?
Isn't oh no, sorry, wrong enough.
Yeah, go ahead. Any questions? That's fine. Let me know.
Could you show that step again, Professor?
So I multiply this first row with -3 and add it to this row and replace the values here. So first row remains as it is, 2, -1, 1, 6, as it is, it remains. Third row will remain as it is not changed. -4, -3, 5, 0, it remains as it is. But for the second row, what I am doing is I'm replacing this row by multiplying the first row with -3 and adding to the numbers here.
Okay. But why did you pick -3 as a number? You can pick any value?
Because I am eliminating this 6 here. I don't want to eliminate only the entries corresponding to X1.
Okay. All right.
That is why I am eliminating 6 here. Now, similarly, I have to eliminate -4 here. What should I do now? You guys know now, right? You just multiply this with 2 and add it over there. Can you help me to find the values? So 2, -1, 1, and 6 remains as it is. 0, 10, -6, and -16 remains as it is. What should be the entries here?
4, 0.
No, it will be not be it. You are basically eliminating this now.
0.
0,
-5.
-5,
7.
7,
And 12.
12. So, okay, so you basically get this. So I'm just rewriting this matrix in the next sheet. Six, 0, 10, -6, -16, 0, -5, 7, and 12. That's it, right? That's what you got, right? So what we actually, is everybody with me so far?
Yes.
Yeah.
Yes.
So what we have done, that we have eliminated all the entries of corresponding to x1 from the other two rows. Only the only entry for the x1 is remaining on the first row. Now we have to repeat the process, and we have to do this for x2. So if I have to do for x2, what I have to do is I have to find R22 and I have to find R32. Can somebody help me to find what R22 and R32 would be?
Professor, a quick correction.
Yeah.
-5 on the last row should be 1.
Why it should be 1?
Because we multiply 2 by -1 and plus 3.
That's 2 or no.
What is the problem?
Sometimes -1.
Which one?
So -5, yeah.
You multiply this with 2. So you multiply this with 2.
2.
And you add it, add it over here.
Oh, I see. Yeah. Okay.
Right? That's
yeah,
what you did. -5, 7, 12.
All right. Perfect. Thank you.
Yeah. So R22, this the same thing, just we have to now find the pivot row corresponding to x2. Pivot row corresponding to x2. When I have to do pivot row corresponding to x2, now I'm not worrying about the first row. First row has already been considered as a pivot row for x1. Now I have to use this matrix or this specific block to find pivot row for x2. So for x2, if I have to find R22, R22 means second row and corresponding to second column, which corresponding to x2. R32 means third row, second column. So in this row, which one is the maximum absolute value? 10, right? And then corresponding to the x2, I have 10 as well. So I am basically going to divide that by the same number. Similarly here, it is basically the maximum value is 7 and corresponding to x2, it is -5. So I'm basically taking the ratio as -5 by 7. Which one is basically greater?
R22.
R22. So it is basically the pivot row is the same as the second row. I don't need to interchange with the third. So it will remain as it is. So if it is remain as it is, now I have to eliminate -5 from the third row. How will I eliminate it?
Multiply by 1/2 to the second row.
Yeah, can you do that and let me know what the answers would be or what the values would be? So I multiply this by 1/2 and add it over there.
Should be 0, 0, 4, and 20.
It will be 10 and 20.
But shouldn't it just be a positive half for your coefficient?
So -1/2 times -6 is 3. 3 plus 7 is 10. So you are multiplying -1/2 for all the elements. So when I multiply -1/2 with 10, I get, actually, it is +1/2, right? Not -1/2.
Yeah. Okay.
Sorry. -3 and -7, it should be
4, yeah, and 20.
And it will be, no, it will be -8 and 12, it will be 4 as well. So minus
That's right.
negative.
You're correct, yeah.
Everybody is with me?
Yes. Professor.
Yeah. So this is what we actually call as row echelon form, where you have basically get an upper triangular matrix. This is basically called as upper triangular matrix. I mean, where this matrix is in upper triangular matrix form. And this is row echelon form. And why it is called a row echelon form basically means this is A and this is B. And how you can solve for x1, x2, and x3, you do back substitution. You do back substitution to solve for x1, x2, and x3. So let me actually again pick somebody from the class. Tuido, am I pronouncing it correctly? 2a into okay, okay, don't have mic, that's fine. So if I have to solve for x1, x2, and x3, let's say I have to solve for x3, how can I solve for x3? Can you help me to find how to solve for x3?
You could just rewrite the equation, couldn't you?
Yes, so I'm asking to do actually. X3, yeah, that's it. X3 equals 4. So basically now if you see this equation and if you actually see and rewrite the equation, you actually get it like this: 2x1 minus x2 plus x3 equals 6. 10x2 minus 6x3 equals negative 16. 4x3 equals 4. So basically you solve this for x3 first. So you got 4 divided by 4 as 1. You use this value in this equation and solve for x2. So it will be 10 times x2, negative 6 times 1 is equals to negative 16. That will give me x2 as negative 1. And then you substitute x3 and x2 value on the first equation, that you will get 2x1 negative 1 plus 1 equals 6. That will give me x1 as 2. So basically you are getting x1 equals 2, x2 equals negative 1, and x3 equals 1. Is everybody with me so far?
Okay, is the next one supposed to be 3?
Yes.
Sorry, come again.
Oh, sorry, there's a negative.
Yeah. Yeah. So yeah, x3 basically, this is what we call as back substitution. Back substitution means you start from the very last row, because you have basically got, if you look at this, this is called as upper triangular form. Upper triangular form means this is a triangle and this is upper triangle. You have got diagonal and you have all the entries below the diagonal as 0. This is called as upper triangular form. If you have somehow the entries below the diagonal and upper elements are 0, that is called as lower triangular matrix. So this is called as upper triangular matrix. Upper triangular. So when you get it as an upper triangular matrix, then you know the last entry will give you, I mean, you can solve this equation for x3, then you can substitute, use the other two, and I mean, you can do the back substitution and you get x2. Thereafter you get x2 and x3, you can solve for x1. That's how you actually solve for x1, x2, and x3. That's how the algorithms, basically, or MATLAB algorithms actually solve any matrix equation. Does that make sense?
That makes sense.
Yeah. So the reason, if I go back and read this sheet again, I was basically showing you, I actually wrote all the steps and I wrote the elementary row operations. And if you have read chapter number 8, you probably have not come across this term, partial pivoting with scaling. And the reason I actually mentioned this specific concept is because this is exactly what you will be learning in chapter number 11. So partial pivoting with scaling is actually the technique that is used in all the codes, whether it is MATLAB, whether it is C, whether it is any numerical library, because this is the technique which tries to avoid the round off errors and other numerical problems that may arise because of only doing elementary row operations. So if you only do elementary row operation, that's what you have learned in chapter number 8, or basically it is what we have learned so far in our previous maths classes. You only do elementary row operations. You do not worry about this partial pivoting. Partial pivoting means you are trying to find the pivot row. Pivot row is the one which actually is used to eliminate the used to eliminate the coefficients corresponding to x1 in other rows. So for example, if you look in this is the pivot row selection. So you interchange that and you becomes, this pivot row comes at the top, and then you use this row to eliminate x1 coefficient from the second row and x1 coefficient from the third row. So you use this row to eliminate the entries of x1 from the other two rows. That is why it is called as pivot row. And the selection of pivot row is, as I mentioned, how do you find the selection of pivot row? You find the absolute value, and then you take the ratio using the coefficient of x1. So -4 divided by 5, absolute values. 6 divided by 7, 2 divided by 2. And whatever the maximum number is, that will give you the pivot row. Once you get the pivot row, you interchange it and then use that pivot row to eliminate the x1 coefficients of x1 in from the other rows. That's what you did. Once you have got that, then you select the pivot row for the x2 coefficient. So that's what we were doing it here. We were trying to, we are not touching it anymore on this row. We are basically using these 2 by 2 matrix, and we are selecting the pivot row corresponding to x2. So we did the same approach. We basically found the maximum value in this row, which is 10, and the coefficient of x2 is 10 as well. So I take the ratio, it becomes 1. Similarly here, the maximum value is 7, but the coefficient is -5. So I took the ratios -5 by 7 absolute values. Whichever is maximum will be the pivot row. You found that this is the maximum. So that means the pivot row remains the same. So why it is called a pivot row for x2? Because I will use this row to eliminate the coefficient in the third of x2 in the third row. So I use that row, I multiply that by half, add it to here. So when I do that, I made it 0. I eliminated the coefficient of x2. That is why it is called a pivot row. And I'll keep on doing that till I got an upper triangular matrix. Since it is a 3 by 3 matrix, so this actually gives you an upper triangular matrix. But if it is a 4 by 4, 5 by 5, you have to keep on doing those operations. And you have to keep on doing till you actually get an upper triangular matrix. And once you get an upper triangular matrix, then you actually do back substitution. That is what you actually have to implement. Back substitution means that use the last row to solve for unknown variable x3, then do back substitution to solve for x2, back substitution solve for x1. So this is what I'm showing for 3 by 3. This is the exact example that is there in the textbook in chapter number 11. But as I said, it is basically the same code that will be used for solving 100 by 100 matrices, 1000 by 1000 matrices, 10,000 by 10,000 matrices, any number that you can think of. We actually use this Gaussian elimination technique. Now, there are many algorithms that are there, existing algorithms that helps to reduce the number of mathematical operations for solving the system of equations. So we'll be learning those when we will be doing, or we'll be practicing those specific concepts in the next few lectures. So today what we actually have seen so far is how to solve, or what is a basic method for solving AX equals B, which is using Gaussian elimination. And it is not only Gaussian elimination, but basically using this partial pivoting with scaling technique. This is the technique that you will find in chapter number 11 when we actually read that chapter. Any questions so far on this?
Professor, quick question. So if we use the Gauss elimination, we would end up with the same answer. So I was wondering what's the point other than because the software uses that method?
No, it is not. Okay, so the question is good, that why do we care about that? So what happens that when you do this type of operations, only this type of operations, sometimes what you will end up with is that you will have 0 at the diagonal element. So if you have 0 at the diagonal element, that basically means you cannot do any type of back substitution. For example, let me just give you one specific instance. So suppose after doing elementary row operations, you are getting numbers like 2 minus 1, 1, 6, 0, 0, 4, 4, and 10, sorry, 0, 10, negative 6, negative 16. So, sorry, I have written it very small here. I just realized it now after looking at the camera. So let's say this is what you actually end up with after doing elementary row operations and not doing the bookkeeping of partial pivoting. So if you end up with this, you basically see that this element is x2, right? X2 has got the diagonal element as 0. Now, if I am doing it by hand, I know that I need to interchange these two rows to get, and I will actually can solve for x2 and x3. I can interchange that and make it just like an upper triangular form. But the MATLAB code or any program that you are doing, they are not looking at this specific form and then interchanging. There has to be certain fixed rules for it to form. A code cannot just look at the numbers and say, oh, I got 0 diagonal, then I should basically see how should I change it that it becomes upper triangular form. So that is the reason that that specific partial pivoting is used to make sure that in the diagonal there should not be any zero or very small entries. If you have very small numbers in the diagonal element on a diagonal, you have a round of errors and your answer will not be correct. Does that make sense?
It makes sense. Thank you.
Yeah. So it is the only reason this specific technique is used is to make sure that the diagonal elements are basically have positive or not positive. Basically, the dominant numbers are numbers which are non-zero. If you have somehow come zero, or the code, any code, MATLAB code, C code, C++ code, any code that actually solves algorithms will never get to know, and it will say the diagonal is zero. You're dividing it by zero. And then basically it says it is an error, infinite numbers, and it basically will give you garbage values. To avoid those pitfalls, this specific technique is used such that the diagonal entries will never are ending up with something which is zero or very small numbers. Okay, any other questions, guys?
First, it's about the homework. How do you want our answers to be turned in? Should it be like in one Microsoft Word, or and what do you want to see?
Yeah, it should be in a Microsoft Word. Yeah.
So the codes and the graphs and the answers.
Yes, yes, yes. The codes, the graph, and the answers. So there is a discussion. There is one section or one point, or I mean one part of the homework is to discuss. So there are some points on discussion as well. So just solving it is not, I'm just copy pasting the graph and just dumping the values is not what your homework should be. The reason that the discussion section has been added is to make sure that you actually think about the problem and physically think about, okay, what the numbers are telling you, what is the story that you are going to get. So you are basically commenting on that story. Are you getting the picture, or what you can make inferences about? So just put some thoughts on the specific problem. That's what you are supposed to do while working anywhere you are working on. Does it make sense, guys?
Yeah, Professor, one
Yes.
question for the homework. So there's 6 different values for the current. So that will be, and there's 3 different methods that we need to use. So
yes,
total of 18 codes. Do you want to see all of them in the homework, or just 3, one of each?
You don't need 18 codes. You are just changing you are using one code for bisection method, and that use the same code to change the values of U for getting different temperatures.
Oh, okay. Yeah, that makes sense.
Okay, so I believe everybody is good. So we wrap it up and for today's discussion, and then we will continue our discussions and on Thursday lecture, and the topics that we are, the topics we are covering are basically chapter number 11. We are still working on chapter number 11. The reason I asked you guys to work on chapter number 8 is to just go through those basic steps, because those are the steps you will basically need when you are doing the concepts, or we are learning the concepts of chapter number 11, which is numerical solution techniques. So having said that, let's wrap it up, and I will see you guys on Thursday, guys.
Thank you, Professor. Thank you. Have a good night.
Thank you. Thank you. Bye-bye.
Bye.
Excuse me, Professor.
Yeah, thank you. Yeah, you have a question, some question, guy?
Yeah, I have a question, Professor.
Yeah, go ahead.
Can you repeat that, please? How we can find the R11, R21?
R11, R21. So here you basically look at, for R11 corresponds to first row and first column. So in first row, what is the maximum value you have?
5.
You do not look at the B, you just look at the A matrix. So you look at this 5, right? And what is the coefficient corresponding to the X1? This is -4, right?
Yes.
So you take the ratio -4 divided by 5. R21. In R21, what is the maximum value you have?
7.
7. And what is the coefficient corresponding to X1?
Oh, X1. Yeah, 6. Okay.
6. So it's 6 by 7. R31. What is the maximum value? Absolute value. Maximum absolute value.
Oh, 2.
2. And what is the coefficient corresponding to X1?
X1 or 2. Yeah, I got it.
Yeah. Okay.